All right, so it's a great pleasure to have Mustafa Amin with us today to wrap up the seminar series. Mustafa did his PhD in Stanford University and went through places like MIT and Cambridge. He's now a faculty at Rice University. He'll tell us about light from dark solitons. Go ahead.
Thanks a lot. It's nice to, of course, give this talk to all of you. It would have been, of course, better to see you all in person. I think I was there about 3 or 4 years ago and remember the visit fondly. Okay, so I'm going to talk about light from dark solitons. And if there are students in the audience, let me start with just a quick summary of what a soliton is. So for our purposes, a soliton is a very long-lived dynamical excitation in a field where nonlinearities are balancing dispersion. Historically, they were probably, it is said that they were discovered by John Scott Russell while he was riding along in Edinburgh along a canal. He saw that a boat came to rest and created a pulse in the surface of the water. And he followed this pulse on horseback for about 2.5 miles and saw that the pulse maintained its shape and traveled at a constant speed without dispersing. So this is considered sort of the discovery of solitons. Since then, of course, these solitons have been found, experimentally observed in optics, hydrodynamics, Bose-Einstein condensates, and of course, they have been put to good use in high-energy physics and cosmology as well. The way the picture on the top is actually a recreation of the soliton in that same canal that John Scott Russell had first observed it. Of course, much more recent. Okay, so that's what a soliton is. For our purpose, for my purpose in this talk, I'm going to be talking about solitons in axions or axion-like fields. There's been a lot of work on this in recent years and also back in the past, where people have shown that localized, long-lived excitations of the field can form quite easily at the end of inflation in the inflaton or in axion-like fields, for example, that will make up dark matter. And these solitons, these localized energy densities that are long-lived, can have both gravitational and non-gravitational effects. I'm mostly interested in the non-gravitational effect of these guys today. And the way we are going to probe their non-gravitational effects is by imagining that the field that this soliton is made up of, let's say it's an axion-like field, it couples to electromagnetic fields via the phi FF dual coupling, or phi E dot B. Because of this coupling, if you take such a soliton and put it in an external electromagnetic field, say near a neutron star, or electromagnetic fields that might be present in the early universe, you might expect a conversion from axions to photons. You might also get axion to photon conversion when these solitons collide with each other, and I'll explain why that happens. And this could be something interesting to explore and look for their observational signatures. So in a couple of recent papers listed at the bottom, led by postdoctoral fellow Zhonggang Mo, who should have been at Rice, but fortunately is still stuck in China because of the pandemic. So he's led this project. And what we did in these two recent papers is we really tried to explore how this electromagnetic radiation that can be generated by these solitonic configurations depends on the details of the configuration. So of course, the radiation should depend on the strength of the coupling GA gamma, but we wanted to explore how does it depend on the shape of the soliton and so on. And what we found was somewhat fun. We found that you can get dipole radiation out of these objects, and you can get some unusual suppression at some configurations, and you can also get explosive production of radiation from these configurations. So I'm going to try to tell you about what are the different regimes in which such different things happen and what their implications could be.
But I'm not sure, because look, it is kind of on particle side, it's just a normal decay, right? So you know this coupling, you can calculate decay rate for the particle, right? Now soliton is just nothing but if you like collection of particles. So the question is that it's coherent, right? Kind of stuff of radiation. So the amplitude could be enhanced, right?
That's exactly right. Yes, yes.
Right, but when you are saying dipole, whatever, then it's about kind of level of coherence. You see, because in this way, it's like, normally if coupling is small, it's like a volume effect, right? You have kind of, I mean, decaying over this elementary particle everywhere in the volume. And if I view it as a collection of particle, then no, I mean, just multiplying by, kind of amplitude, for example, if it's coherent. But you are talking about some more detailed effects, right?
No, I think the dipole radiation is like that. That each point I can imagine that just and first of all, so it's not just a decay, right? It's also it's axion photon conversion, right? It's one axion. I mean, if you're an external electromagnetic field, it's not just decay, right? You're converting from axions to photons in the presence.
But this would go only if your external field is kind of noticeable, right? Because if it's perturbation, right, then it's just decay.
That's right. But I think so. I'm imagining some situations where the external field is noticeable. For example, near white dwarfs or neutron stars, it's very significant, right?
I see. So in this way, it's both solitonic nature of this object and external field, which is electromagnetic, right?
Exactly.
But the very notion of existence soliton, I would say, for me, would be in doubt, because why axion would form soliton is not it's not given for granted, right?
It's not given for granted, but I think and I'll talk about this in a moment again. If you take a potential that has attractive self-interactions, the axion potential has attractive self-interactions, or just because of gravity, it doesn't seem that difficult just from generic initial conditions to form these localized structures. Mm-hmm. Now you could of course argue whether how likely are these objects to survive till today. Right. That's a much more that's a very
I meant stable. Yeah, to get a stable stuff, it's not easy.
Absolutely. And I will certainly mention this in more detail in a few slides, and we can.
Mm-hmm. Okay, I'm sorry to interrupt. Thank you.
Thank you. Thanks for the question. Okay. So this slide, of course, is an obligatory slide. There's of course excitement in trying to understand axions and its couplings, axion-like fields and their couplings and so on. Okay, so just having given you this, what I'm going to talk about more broadly, I want to next just give you a little bit of orientation. I want to talk about the physics of soliton formation, stability, and clustering, but this is a talk in itself, so I will delay that a little bit to later so that we can discuss that more. But I will come back to that as well. But mostly I want to focus on this production of light from these objects. Okay. All right, so just to put these things in context, these solitons could be forming after inflation and before the CMB in the early universe, or they could be forming in dark matter in the present day universe. The mechanisms could be quite different, and depending on when the mass of these axions or axion-like particles is, their scales could also be very different from each other. So for example, if these things are forming in the early universe, and this is, then their scale is obviously going to be microscopic. If these solitons are forming today, then their scales could be macroscopic, but still smaller than the scales of galaxies, but certainly. Okay, so to discuss a little bit more about the solitons, let me first say that everything I'm going to be talking about today is going to be limited to this action. It's going to be limited to just a real valued scalar field with gravity, along with electromagnetism and the coupling phi FF2. So this is my playground for everything I'm going to say today. And first, let me just talk about the scalar field part of this action, okay, which is where I'm going to first introduce what these solitons are like. So in this scalar field part of the action, there is of course one relevant bit that is not specified yet, which is the potential V of phi. If we are talking about an axion, a typical V of phi we would pick is 1 minus cosine phi. That's a typical axion that we talk about, but I'm going to allow it to be more general and imagine that you could have different potentials here for axion-like fields, but all of them, almost all of them, I will consider that either they're purely quadratic or they are somewhat flattening away from the origin, meaning they're quadratic at the minimum and then they have wings as they move outwards. This, for my purposes, these essentially are providing an extra attractive interaction that can hold objects together in addition to.
But you in this form disregard by gravitational interaction, right, per soliton?
Sorry, no, I can have gravitational interactions as well.
But it's not written in your action.
R?
Your action doesn't contain it. No, it's not interaction.
I mean, but it's interaction in what sense? I mean, isn't it, gravity is there, right, with the Ricci scalar?
It doesn't help if there is no coupling between phi and gravity.
But there is, there in the kinetic term there is.
There's a kinetic term.
Kinetic term, then it's not, then here it implies that it is associated with G mu, right? So it's there. Yeah, it's what I'm checking, right?
Oh, yeah, sorry, I didn't realize. Okay, yeah, of course, there is G mu here, right?
Yeah, okay.
Okay, so these types of potentials with or without gravity can support these long-lived spatially localized excitations, right? That can be incredibly long-lived. And let me just talk classically first.
Okay, I'm sorry to return a little bit back. The reason I ask it because if it's kind of conformal theory, then there is also term R phi square, you know, besides the G mu in kinetic term, right? But probably it's not important for you.
Yeah, I'm not using that, right? So this configurations are localized, you know, they're spatially localized, they're oscillating in time. And if you're just thinking classically just with the scalar field objects, if you were to take, say, just a cosine potential without, imagine you're doing this without gravity first. Okay? If you do it without gravity, then these things don't last more than, say, 1,000 oscillations. However, if you take a slightly different potential, say you take a potential that looks like, you know, something that flattens out to 1/2 or this log potential, okay? Even without gravity, it has been shown that these things can last for hundreds of billions of their oscillations and even longer. Okay, so classically they don't want to disperse off. If you include gravity, depending on the amplitude, again, you can have incredibly long lifetimes for these objects. So that's something that partly you can show analytically, although this is a little bit, there are caveats to that, but also numerically, if you just put them on a computer, they will last for billions of their oscillations, and you can keep on tracking them and they don't go away. You can perturb them a little bit, they still stay in place.
Sorry, can I ask here, so what boundary conditions are imposed here on the boundary of this region? So
depending on the simulation, typically if you are doing a very long time one, we do absorbing boundary conditions. So we take away the radiation out. Otherwise, you know, it does, for a very long simulation, of course, you run into trouble because the radiation comes back in.
Yeah, that's why I'm asking, because if it's, if they're not outgoing, then it's easier sort of to make it.
Yeah, so, but we do include that. So especially, and we've also done something where we actually tried to do analytic calculation to figure out why it's so long-lived. And we find essentially that the leading mode that you would expect this stuff to radiate into is essentially shut off, okay, because of the shape of the configuration. So it's not in the Lagrangian itself, it's really the shape of the configuration that's shutting off the outgoing radiation.
But it is not exactly like soliton, right? Because it's kind of blazing mode, right? But I mean, like, it's not like a stable soliton.
It's not a perfectly stable soliton. So I'm using the word soliton like it's long-lived, right? Yeah. It's not perfectly stable, and it shouldn't be. I mean, there's no conserved charge here. There's nothing or topology to really protect it. Okay.
But this is some kind of localized excitation?
Yes, so it looks,
Rather than,
yeah.
rather than being coherent oscillations in a coherent field.
what do you mean?
I think these are coherent oscillations.
This is coherent,
Yeah.
right? I'm not sure
Yeah,
why.
it is. It is
Well,
still. It
But
is
it's
still
localized
coherent.
in space. The X and Y here are the space-time coordinates.
Yes, yes. They're space-time coordinates, yes.
So you have it localized in one space, in one place.
Right. So
As
this
opposed-
is this space, X and Y are both space. I mean, of course, there's a Z-axis as well in the same way, but they're
Sure.
localized in position, right?
Right.
They're about, about, depending on which, they can be a few M inverse, where M is a mass in size, up to, thousands of M inverse in size.
No, but if it's say excitation, whatever coherent excitation, what is a ground state?
So I mean, coherent.
So the ground state would be that just flat, or no, I mean
Just flat.
excitation on it's relative to what?
Right. So, I mean, the ground state here would be, if there's nothing else, I mean, it would be flat, right? So I think of this as a solitonic structure because of the fact that it's, actually, let me put it another way. This is by itself, you can think of this as a separate state by itself, right? I don't know if I would think of this as an excitation around, a small excitation around flatness.
No, but look, either it is like classical initial conditions that I collect some number of, kind of this coherent, field at some point, and then look how it behaves afterwards. Okay, this normal soliton, it means that I choose such a coherent configuration of the field which lives forever. Then the ground state of this would be just a stable configuration, right? Which could move as whole, but it would be not just. That doesn't look exactly the way you are describing, right? Because your oscillation, it is not like a motion of soliton, right?
Yes. So I think I can say that. So the first part you said, right? So yes, it is in this sense. You start with this initial condition, you put it in place. It will stay in place, and it will keep on oscillating for a long time. Even if I gave this a little bit of a boost, okay, it will still move around with the same oscillations. It would move around. So in that sense, it is similar to a soliton.
Right, but it is still. I mean, then in terms of how say there's particle-like solitons, and the one which is like a real analog of particle state, right? You have say monopole, or you have domain wall, right? So it's not of this kind of status, right?
I think it's not of that kind of state, right?
No.
This is, I would think of it like a cue ball. It's closer to being like sort of like a cue ball, right?
Yeah. It's what I'm asking.
But then so the relation that here the field is real, right? So you can try to explain its long-livedness by relating it somehow to the complex field configuration where there is a conserved charge.
Yeah. So I think it's under what you said is absolutely right? So if you actually think of this object, there is an approximate conserved particle number. Okay, it's not exact like in the cue ball. It's an approximate, just because it's non-relativistic. So number changing processes are very limited, and that's part of the reason why this object is very long-lived.
Mm-hmm.
So it's approximately conserved. It's not like a cue ball where it's if you just had the complex field. All right. So this actually brings me exactly to what I was going to say in the next slide. So these objects, as Professor Weinstein just asked me, right? Like, so these objects could exist without gravity if if you just had a potential that was opening up away from the minimum, and that means the self-interactions are supporting it. Then it's just got a name. It's called an oscillon. If it is only gravity that's supporting it, it's called an oscillaton. And in this region also, you could have dilute objects or dense objects. By dilute ones, I mean that if you think of this potential shape and say the scale where the potential goes from quadratic to flatness is some scale f, then the dilute ones, the amplitude of the field at the center is small compared to f, and the radius is much larger than m inverse, where m is the mass at the bottom of the potential. In the dense regime, you are in the opposite regime where the amplitude is of order f and the radius is of order m inverse. Okay, so these are different regimes in which all of these regimes, these objects can exist. So it's not just that given some parameters, there's only one object that's stable. It's usually a family of these objects that can be. And Andre, as you asked a moment ago, right? So these are connected. So these objects which are in a real valued scalar field are of course similar to cue balls which are present in complex valued fields. And if you include gravity and complex value field, of course, those are often called boson stars. So these are connected to them, but just this is all in a real valued field.
But also, can I ask, so in terms of lifetime, what is better, dilute or dense configurations, which live
So
longer?
dilute ones will be better. Okay, dilute ones are longer lived. The dense ones, it's a self-interaction. What happens is that the self-interaction that is holding them together in the dense case is also responsible partly for making you decay. But they can, as I said, like it's billions of oscillations is easy to get. It's not so hard.
But when you're talking about this complex field, you know, it could not be then this two-photon vertex which was before, right?
Yeah. I'm not going to talk about the complex field at all. I was just trying to make a connection that it is related if you want, if people are familiar with that, with the complex field case. Of course, absolutely, it's not needed there. Okay, so now let's talk about the photon production. And again, I'm going to go back to my real field, which is what I want to deal with. Okay, so this is again just review for most of you who've seen this before. So Maxwell's equations just classically get modified because of the presence of the axion. You can think of the axion field, even in absence of free charges, inducing a effective charge and current density. And the Klein-Gordon equation for the axion-like field will also get a source now, which is E dot B. So this is the way the system is modified. Again, if you wanted to include gravity, at least perturbatively, then you would just, in this equation here, you would add 1 plus the gravitational potential. You can do it more generally with GR and include the contribution from the electromagnetic field to gravity as well. But for our purposes, that's not necessary. We are not in the regime of GR, at least for the moment. Okay, so what happens to this system? So if we look at the system of the Maxwell's equations, now just written at second order now, in second order form, the presence of the axion, and in particular a spatially localized oscillating field configuration, will lead to a spatially localized and oscillating effective charge density and effective current density. So this oscillating field gives you oscillating charge and current densities, effective charge and current densities, which, as you might imagine, should give rise to electromagnetic radiation from here. So I'm just thinking classically, and this is not so difficult to see from the equations themselves. Now, a little bit more careful assessment of these equations, you look at these E and B equations. The rho and J are linearly dependent on the axion field.
No, but it's also contain, you're implying that you have also external B and E, right? Because, you know, if there is no B and E, then this rho and J equal 0 as well.
That's true, but you will always, I think at the very minimum, you will expect to have some quantum fluctuations of.
No, but then you cannot call it normal radiation. It's still different, right? Because it's true. Like decay.
That's very true. That's very true. I think so you're absolutely right. So if I'm talking about this classical radiation, I need E and B to begin with. But we'll see that even if, in some ways, what will happen is even if we start, because of the fact that this field is oscillating here, even if you start with very small amounts of E and B, this oscillating axion field can basically lead to a very rapid enhancement of whatever small amount of E and B fields that you put in there. Okay, and this is just a resonant effect, which I'll discuss in a moment. And that can give rise to, then you can interpret again as a classical radiation because the occupation number will become large. Okay, so.
But the naive question, so can you make configuration with internal E and B each kind of supports in being
What do you mean?
without external fields, just real field plus some classical electromagnetic.
I haven't constructed something together. So what I always have in mind is I have so there are two situations I will have in mind. One is where there is a soliton just of the scalar field and it enters a region of an external E or B field, and we see what the effect is. The other thing I'm going to imagine is that I have a classical configuration of the axion, and then there are small fluctuations of E and B field that could be there just from starlight or just from quantum fluctuations, right? It's not part of, those things are just there in the background, and I'm going to extract energy from there. And I'm going to enhance them by converting the axion into photons.
You can say that interaction with soliton, it's like changing your Maxwell equation, because put this, say, rho G, it is linear in field, right? So I can say that it is like a modification on Maxwell equation with coefficient, say, which are space and time dependent.
Absolutely, right? That's exactly what I was trying to get.
And it is, and I believe that it is correct approach when you're trying to discuss production of the field.
Exactly. That's exactly right. So the fact that it's linear in E and B, that structure of the equation then helps you understand, that production of the field, whether you have background fields or not, will.
Yeah. Right.
Okay. Good. So this fact that the equations are linear in E and B, and they have periodic coefficients, this enters the domain of Floquet theory. So we know that we should expect two types of solutions. We should accept steady solutions of E and B, and we should expect also exponentially growing solutions. Okay, there are two possibilities here that we are going to get along with some boundary cases, but we'll just think of these two cases. So what are the conditions in which you get one solution as opposed to the other? So to understand which regime we are going to be in, whether you are going to get the steady production of electromagnetic radiation or whether you are going to get this exponential production, you want to compare two timescales. The two timescales we want to compare is suppose you produce some photons, okay, in the region of the soliton. There is an escape timescale. How long does it take these photons to leave the system? And then there's let's call it the Bose enhancement timescale, right? Where you are going to produce some photons. If they're hanging around for too long, that mode is already occupied, you're going to enhance it. Of course, this can be thought of just classically from the picture of parametric resonance. You don't have to think quantum mechanically here to do that. And you can calculate the ratio of these two timescales. So the top timescale, which is the escape rate, is just the radius of the object. And then there's what is called the Floquet exponent. In Floquet theory, you can also calculate that for this system. And it turns out that this number, again, it should really be a twiddle. It's this product that controls this dimensionless number. So it's a product of the coupling, the field amplitude, the frequency of oscillation, and the radius of the object. So it's this combination that controls whether you are going to be in a regime where you're going to get the steady radiation, or whether you're going to get exponential radiation. Now, this, just to sort of orient ourselves again, this omega here is just the frequency of oscillation, which is roughly just the mass of the axion-like field. Phi naught is the amplitude, and r is the radius. You can see that either you can have the amplitude times g. I mean, you can control this number by controlling the product omega r versus g times phi naught. So you can have a very large configuration with a low amplitude, or we can have a large amplitude with a small radius, and they could give the same type of C. So in general, if this dimensionless constant C, that is the ratio of these two timescales, is very small compared to unity, you have the steady radiation coming out. If this ratio becomes comparable to unity, you're going to get exponential radiation. So this is a nice, sort of a simple picture of which regime we are going to be in. Depends on this dimensionless ratio here. All right, so now let me just show you some explicit results. So this first, I'm going to be dealing with the case where this dimensionless coefficient C is small compared to unity, where we expect these steady solutions. And I'm going to operate in the regime where there is an external B or external E field, okay? And I can do a calculation to leading order in GA gamma phi naught, just a perturbative calculation. And this just, in this case, you can pretend that this is just a source, an electric or magnetic, oscillating electric or magnetic dipole. Open up your favorite textbook and write down the formula for dipole radiation in this case. So you can get how is the power radiated from the system quite easily this way.
But you could instead consider the case where there is no external B and E, still consider your resonance, right?
Yeah, absolutely. You can still do that. Yeah, there's no need to have, and I think I just want to do two cases separately, and to just show the different regimes, and I'll connect them. I'll connect the whole picture together as well. Yeah. So one of the main things I want to sort of focus on in this condition where there's an external E or B field is that the amount of power radiated depends, the amplitude depends on the Fourier transform of the spatial profile of the object. It's an antenna, it should depend on sort of the spatial profile. And where is the Fourier transform supposed to be evaluated? It's evaluated at the wave number equal to the frequency of oscillation of the system. That's where it needs to be evaluated. And that's what controls the amplitude of the power that is radiated away. It's of course proportional to B squared, as you would expect in dipole radiation, and sine squared theta, the usual way. So the reason I mentioned this, that this gives us an immediate indication that the dipole, so what I'm plotting here is this Fourier transform phi squared of omega versus the radius of the configuration. So it tells you that to get efficient dipole radiation production, you need these objects to not be too fluffy. They can't be too large in size. If they're large in size, then you get an exponential suppression because of the size of the configuration. So there's, I could think of this, if this is just, if I think of this as Huygens principle, that each region is radiating something, then it's interference effects that are causing you to get suppressed when your system size becomes big. And so there's this blue line is that exponential suppression. All the other gray lines are just some different profiles you can pick for the object. But the blue line is what is the realistic case.
But the size is big compared to what? Compared to mass, inverse mass?
Compared to M inverse, yes. So omega is roughly always M inverse, right? Omega is just M, sorry. So the size is big compared to M inverse. Then you are going to get suppression of this dipole radiation.
Okay, but then it's really like a collection of point sources, right?
It's not quite, yeah, it is still a collection of point sources, but not, I don't know in what sense you're saying it's a collection of point sources. If I just took a collection of point sources that are incoherent, you would get a different answer though.
No, but does it imply that your density of axion is such that you have not one axion in the size 1 over m, right? Because if you have just one axion per size, so it implies that one mass is sufficiently small, so your packing is inside of wavelengths, right?
Yes, that's, I'm packing, I think you don't have to be, yeah, so you have to be on scales that are not too different from the Compton scale, I agree.
Yeah.
You have to pack a lot of them on top of each other, right, for you to get significant dipole radiation.
I see.
Okay. So here's, Arkady, here's what sort of will answer hopefully your question of connecting it to larger amplitudes on this slide in a moment. So first, let me just show the power radiated in an external E or B field as a function of this parameter C, this dimensionless parameter C. And the black line is a dipole estimate. What we ended up doing is we ended up doing a numerical simulation on a lattice to just see what happens as we make this coupling large so that we are not in some perturbative regime here. And in the presence of a background B field, we find that it agrees with the dipole estimate at small values of this coupling, but it starts getting suppressed actually at moderate values of the coupling. We are still in the steady regime. We are not in the exponentially growing regime. We still have a background B and E field, or E field. And you see that there is non-trivial behavior as you increase the size of this coupling C. Indeed, not only that, if you actually look at the radiation that is being produced, you even find that the dominant frequency at which you're radiating electromagnetic waves also changes as you go from the small value of the coupling to large values. Here, this is radiation essentially at omega. Here it is 2 omega, here that you radiate the field. So there's non-trivial structure that happens as you start going to larger values of coupling. This is the same thing done now for an external E field instead of external B field. I must admit, I can't actually do the analytic calculation to figure out this suppression. Like I'm relying on the numerics to tell me this. I can make some hand-wavy arguments that I don't fully buy, which is that, there's something like a Lenz's law at play, that the generate B field is in the opposite direction of the field that produced it in the first place, but it's not complete. I can't really justify that in detail. Okay, now finally, now let me go to the regime. So this is all in the regime of external B field and small to moderate couplings. Now let me go in the regime where this coupling C becomes large enough that you enter a regime where it's exponential. So this is what was already discussed earlier, that in this case, you should really treat this as modifications of Maxwell's equations, where the coefficients are time and space dependent, and not think of this there being an external source really. And in that regime, you will see that you will get an exponential growth of the E and B fields, even if you start with very small fluctuations. You don't need to source it with a background E or B field whatsoever. So that happens when this coupling C becomes order unity and a little bit larger. And this exponential regime can be efficient even if you have a large fluffy configuration, which is much larger than size M inverse. This is different from the dipole estimate, right? The dipole case only worked. You get significant radiation only when the size of the object is not too large compared to M inverse. But for this exponential regime, the size of the system can be large, and it can still work. So
but there also could be some saturation. I mean, when you are in this parametric regime, it doesn't mean that it will go exponential all the way.
It doesn't. Actually, it goes exponential until it extracts about order 1 energy of the axion configuration. Yeah. And then it back reacts. It shuts down, it settles back down. And we have done, I can show you the simulation actually of what that does, absolutely. But it extracts an order unity energy of the axion configuration before it shuts off. Right? So it's a significant fraction of the energy that gets extracted in the exponential regime. So here is actually a fun example of that exponential regime. So what you're going to see is initially I have 2 blobs of these axions. Okay, the density is in blue here. And the initial configuration is such that this parameter C is less than 1. So they're not in the exponential regime. So they're not really radiating much at all. Okay, and there is no much electromagnetic field. But you will see that when they merge together, something dramatic takes place. So the right-hand side is the production of photons, the energy density of photons that have been produced. So you notice, and this I've stopped the movie here. If I let it run further, it would settle down again and stop radiating too much. So what's going on is that before the collision, the configurations are such that they're not in the exponential regime. As they merge together, you suddenly pass this threshold that I was discussing here into the exponential regime, and you give out a burst of electromagnetic radiation because of that. So this is.
But I think that it is some kind of internal contradiction then in your title, like a light for dark matter, because then it's not a dark matter, it's very bright matter.
Yes, it is. But it's great because even So I think it's still dark in the, I would say that the GA gamma coupling can still be small as long as this whole parameter is order unity, you can get it, you can get it.
No, but it is like a flashes, right? Then.
It is absolutely, absolutely. Yeah, so it's, if we, I would be, I mean, if this is seen in nature, it would certainly be spectacular. It would be spectacular.
Sorry, can I, yeah, so this phi 0, yeah, I mean, it passes threshold, but then can I think of some, you know, average energy that is, if it's bigger than some critical energy, then it's unstable and it decays exponentially fast. And if it's smaller, then it's, then it lives long enough. So, because, yeah, I see this dimensionless coupling, so it's proportional to phi 0 and R, right? So these are crucial parameters. And they change, but can I use something which is maybe which is more clear? I mean, like energy or something like that, the energy of the configuration.
I think it's I don't know if I can make that argument in terms of energy, because it really, at least my understanding so far, is based on these two timescales, right? Escape timescale over the Bose enhancement or this parametric resonance timescale. So I don't know how I can tell you in terms of energy. Because
if it's just proportional, for example, if phi 0 energy grows, when
oh,
phi 0
I see,
grows. Yeah.
Oh, I see. That's what you're asking. Sorry. Yeah. So phi 0 is, so in terms of the energy density of the configuration, right? You should think of phi 0 squared R cubed gives you the energy density.
Right.
So because that's just the, that's how you would get energy density. So you could replace, depending on how you want to do it, you could replace phi 0 or R with an energy density here. But it's not like I can just replace it by energy density alone to get that.
Okay, so C, the C is not, in general, is not monotonic function of energy density.
It's not, but in the regime, it depends on, so let me put this, in the dilute regime, the field will go as 1 over R squared, okay? So the field amplitude goes as 1 over R squared. That's in the dilute regime. That's roughly the case. In the dense regime, the field amplitude is somewhat independent of the radius. It's almost constant in that region. So those are the two things that I can tell you. And then you can convert that by using phi naught squared R cubed. You can convert that to energy density.
So can I ask a question here about this burst, this explosive burst of radiation?
Yes,
I mean,
please.
if this is coming from dark matter, then it would be problematic if this occurred, for instance, after Big Bang nuclear synthesis, because you could bust up all the elements. So
yeah, absolutely. I think
so then are you going to talk about like the limits on the couplings on, is that what?
I think I haven't done the analysis, but I think the difficulty would be, not the difficulty, but one way for why this might not be so concerning is because two of these objects finding each other is not so easy, right? They have to collide. They have to merge together. So
the frequency of radiation is still limited. It's not in the gamma ray frequency, right?
Yeah, and it's like the mass of the
it's a soft radiation.
That's very soft radiation.
You may overpopulate photons or do something, you know, with an effective, but not with the elements where you need hard radiation.
I see. So the frequencies here are not sufficiently high enough.
It's limited by MA. I don't think you can get more, maybe some several MA, but at most, right?
Mm-hmm.
Yeah.
I see.
Absolutely. Yeah. Sorry, I should have said that actually. That's a very, what Maxime said is absolutely right, right? That's, the radiation is just coming out at the mass of the axion. That's the scalar. You're not going to get frequencies much above that from these things. So whatever you pick your mass of the axion to be, that's the frequency at which you're going to get radiation.
Yeah, but you could have heavier axions in the GeV range, and then there were constraints, right? I mean, people talk about all sorts of things in the early universe, because you're not limited here to it being, well, you're just limited to a population of axion-like particles, right?
That's right. A population, I mean, what I'm limited to is how many of these solitonic configurations are around.
Yeah, but coming from a population of axion-like particles.
That's right. Yes. Yeah. Yes. That's all I'm limited to. Okay, just to give you, this is a little bit of a model dependent number, but I'll give it anyway. This is coming from the simulation. So about when these things merge, about 30% of the total energy that you started with goes into scalar axion waves first, and about 20% of what is remaining once they merge together goes into electromagnetic radiation. But this is model dependent and somewhat configuration dependent, because this is for, remember, two objects in the axion field that are trying to merge. They have another degree of freedom internal, which is the relative phase. So if the relative phase is close to pi, then they don't merge very easily. They bounce off each other. So there's and if the relative phase is not pi, then they merge, but they can merge in different ways. So this is a little bit of a model dependent number, but roughly gives you a sense of what this should be. And at the bottom of the page, I've just picked some values. This has nothing to do with what is likely or realistic. I've just picked some numbers to give a sense of how much energy this would mean. And this goes to Maxime's point that he just mentioned, that the frequency is roughly of order the mass of the axion, whatever you pick it to be. Okay, this is a small digression from what I've been talking about electromagnetic radiation from these objects. You might wonder whether these things, if they're dense enough, and if I choose the axion parameters to be such that they can be massive enough, that they might generate interesting gravitational radiation. So this work, by the way, and I also wanted to mention this work because it is done with
I'm sorry to interrupt, but you showed these numbers for frequency on the here. So is it what it is? It is visible light, or this frequency? What is the band?
Radio. This is radio.
Radio, right? So it would be not visible then.
Yes, it would not be visible, but this one, radio, I mean, telescopes would be, if this was a flash, it would be possible for telescopes to detect them.
I see. So no, it's what I was trying to find out. Yeah, thank you. I see. Mm-hmm.
But again, this completely depends on what mass I picked for this, right? So it's that I haven't, but this 10 to the minus 5 eV is in the radio.
Mm-hmm.
Okay, so this work is now, I'm not talking electromagnetic radiation, I'm going to be talking about gravitational radiation from these collisions. And this work was done in collaboration with Marcos Garcia, who was a graduate student with Keith a few years ago. And he was also a postdoc with me for a couple of years ago at Rice. And it was also the other person who did the work, who did the numerical simulations, was Thomas Helfer, who was at that time a graduate student in King's College London. So this one, this was done before the electromagnetic work, even though I'm telling this as part of the story. But I thought it would be just worthwhile to mention that if these objects collide together, you can also, of course, you would get gravitational waves, but there's some interesting regimes of what happens depending on the type of configuration we have. So here again, I'm not talking about electromagnetic radiation. I've shut that coupling off because this is just gravitational. So here, this is just the density of the objects. So I'm showing them that they're colliding. These are ultra-dense objects, and this is done with full numerical GR. And on the left-hand side, you are seeing the waveform of the gravitational waves that you would see from the collision of these guys. So they don't settle in immediately, and they oscillate for a while, so you see these bumps and wiggles in the waveform. You can make them sufficiently compact. This is not so easy to do, but let's say we start with initial conditions that they are sufficiently compact. In that case, if you collide them, before collision, they are these nice solitons. After the collision, they actually collapse to black holes. So the flashing is numerical. But
if it's not like a kind of black hole formation or whatever, I would be kind of expecting that it would be a weaker source of gravitational wave compared to, say, two black holes, or say, merge. So, because I mean, just because of amount of energy there, right? So in this way, I mean, you can have this gravitational wave, but it doesn't mean that it would be kind of in the range which is possible to detect, or what I wonder about?
Yeah, so let me just show you this slide is exactly that comparison. So if you have two objects that are fluffy and they don't merge to form a black hole, okay, in that case, the gravitational waveform is this orange curve in the leftmost plot. So you notice that that's the amplitude. Initially, there's a burst, and then it sort of little ripples afterwards. The black curve is the same calculation, but for corresponding mass black holes.
Mm-hmm.
So you notice that one is smaller than the other.
Uh-huh.
The fluffy ones is, as expected, it's smaller than the other. It's not so much because I'm assuming that they're the same mass as the black holes, but because they're not as compact, they're not able to produce as much gravitational waves as the black holes would. This is again for head-on collisions. Then I've done the same thing in the next two plots. This is done with those guys colliding and forming a black hole, or them being so compact that even perturbations will make them into black holes before they collide. So that's the rightmost plot, where it's indistinguishable from black hole, for obvious reasons.
Right, but then it's more or less the same as black hole.
Yeah. So that region is just a sort of a check on our simulations to make sure that we are getting the same result as you expect. But the critical case is somewhat interesting because, as I'll show you in the next case. So in the case when they're fluffy, you get radiation that's somewhat less than black holes. The black hole line is the dashed line here, corresponding mass black holes. But in this regime where you merge to form a black hole in the middle, you can actually get radiation, gravitational radiation, that is larger than corresponding mass black holes. This is likely because these objects, they form a black hole after merger, but they're a little bit more deformable than black holes before merger. So the quadrupole moment can be slightly larger before they merge to form a black hole. So you can get a regime where their gravitational waves can be larger than corresponding mass black holes. Again, my important caveat here being that this is all done for head-on collisions. We haven't done in spirals, which is a more realistic case. And then it nicely returns back to the black hole case when they form black holes before merger. The other thing to just notice that this percentage in gravitational waves is quite small. It's nowhere close to order unity energy density of these objects, which was there in electromagnetic waves. So this gives you some sense of which ones will be more dominant. Okay, how much time do I have left?
Well, 5 minutes in principle, but usually we go over, so I'd say it's okay. But we can ask the room if people need to leave soon or not. Okay.
I'll try to see if I can get to my main story, but feel free to. I mean, I can continue depending on what the.
Mm-hmm. No, I would say just go ahead. Yeah.
Okay. So far I've been talking about all of these things, making a pretty an assumption that this is all happening essentially without a medium. There's no plasma. Okay? But if I'm thinking of applications around neutron stars or white dwarfs, I have to think about there being a plasma surrounding them. So you have to think about what the effects of the plasma is. What I'm going to say next is not new. Like this, effects of the plasma have been well studied, but still I wanted to put this in the formalism that we had. And one of the interesting things that people have noticed in this regard before is that if the plasma frequency, okay, which is related to the number density of the charge carriers, the lighter charge carriers, if the plasma frequency matches the frequency of oscillation of the system or the mass of the axion, then you get another type of resonant conversion. Okay, this is not the parametric resonance one. This is just you're matching the energy. And that can lead to a significant enhancement of power also. So imagine this soliton sort of falling into a neutron star. And if there is a radius around the neutron star where the plasma frequency, which should be a function of the radius, matches the axion frequency, that can also lead to a burst of electromagnetic radiation because you get significantly enhanced when the frequency of the plasma matches the frequency of the soliton or the mass of the axion. Because this is another effect that's, I think, interesting and it can be easily worked out. just some numbers again, so that I'm not talking completely in terms of free scales. So here's some numbers for the mass of the soliton, again, picking some arbitrary numbers for this scale F and the mass here, as well as the radius. This is in the dense regime. If you want to, you can also calculate how many interactions such objects would have in today's universe with, say, white dwarfs in our galaxy. And this gives you a rough estimate of that number. Again, these numbers are very changeable depending on what parameters you choose. This is roughly the amount of flux that you would get from these objects. This flux is actually, if one of these objects, one of these flashes that I was talking about happens nearby, it should be very easily visible. But it depends on whether it happens nearby or not, and whether these objects actually are there in our universe in the first place. Okay, so let me just, before I end, I do want to talk a little bit about formation mechanisms. It's just 1 or 2 slides, but feel free to ask me detailed questions about the formation of these objects. And one of the things that's interesting about these objects is that they seem to form rather easily. The simulation I'm showing on the left is actually, you start from almost homogeneous initial conditions, but you have strong attractive self-interactions, and that leads to formation of these objects quite easily. People have also seen the formation of these objects just gravitationally, by just Bose condensation from arising out of fluctuations over a long time scale, or forming in the center of halos and so on. Of course, if it's forming in the center of halos and so on, usually the size is pretty big. It's not something that's, it's not a small size object that forms.
Does it imply that, like some people think that dark matter is the same as axions?
Yes. So in this case, so if I'm talking about this forming in halos and so on, its dark matter is assumed to be the axion. Yes.
I see. Okay. Thank you.
But in general, it doesn't have to be. Again, everything I've said so far is about scalar fields in general.
Mm-hmm.
Yeah, let me skip over this, as it's usually just a technical point that it's hard to do simulations over long time scales. So usually you want to integrate out fast modes and write down some effective non-relativistic theory Schrodinger-Poisson-like equation. But let me skip that for the moment. Okay, so just to give you some idea, this is a one-dimensional simulation. I've shown you 3-dimensional results already, but just that how easy it is to form these things as long as the instability growth rate is large compared to Hubble. So the top one is a homogeneous initial condition, almost homogeneous with some small fluctuations. You see the formation of these structures quite easily. The bottom one was from somewhat more random initial conditions. And again, they can form relatively easily. It gives you some sense that this is not so difficult to produce. Of course, there are conditions on how they form and so on. The more difficult thing is, in my view, not formation, but whether they can last long enough, especially if you're thinking about massive axions, not ultralight ones, then even if they last for billions of their own oscillations, that can still be short compared to astrophysical timescales. So this is all fine in the early universe where they will last because their lifetimes are long compared to the Hubble timescale then. But if you're trying to do implications in today's universe, you can't easily rely on these being produced in the early universe and then surviving to today. You want to form them today to take advantage of them. Otherwise, they will. I don't think they'll last that long. Okay. This, again, please ask me about it. This is not about what I talked about, but about CMB birefringence caused by axion strings in axion-like particles, cosmic strings, essentially. But I'll skip over this and try to end here. So just to summarize, I've told you about, what is it that determines whether you get steady radiation or exponential radiation from solitonic configurations when they're coupled to electromagnetic fields. Hopefully I've given you some parametric understanding of how that happens and shown you that this agrees with detailed numerical simulations that have already been done in this context. Observationally, a lot of work still remains because I think to really make observational predictions, I need to give you a population of these objects that survive today. And what the frequency of that is. I can give estimates for that, but I think it's still a work in progress that needs to be done more carefully. In the context of the early universe, as Tony mentioned, it would be interesting to, I think, study what their implications would be. We haven't done that yet, but it would be worth considering and seeing what that does as well. So with that, let me end here and take questions.
Right, thank you very much, Mustafa. Here's some virtual applause. Any questions?
So I have a question about the lifetime. So what goes into the estimate if I'm assuming an axion-like particle that is massive?
Okay, so it's hard for me to give a clean answer to this, but I'll try. So the lifetime is in units of, I'm going to give you lifetimes in units of m inverse, okay, where m is the mass of the axion. It's not something that you can read off directly from the shape of the potential. If somebody just gives it to you, I can't tell you what the lifetime will be. What you need to do is you need to try to find the family of solutions of these objects. And as you scan these family of solutions, what you will find is that for certain configurations, the dominant decay channel into scalar radiation vanishes. Okay, so you can actually write down the decay channel, and the dominant decay channel vanishes at that point. And when the dominant decay channel vanishes, then your decay rate is determined by the subdominant one. And that's what essentially gives you the lifetime of the configuration. So it's not an easy answer because I can't do it with Feynman diagrams. I have to do it, you have to rely on actual configuration to calculate this. So it can't be read off from the Lagrangian itself.
I see. So when you say the actual configuration, do you mean that if I fix a theory, meaning the potential, the mass, and everything, then all of the solitons that I form would follow exactly the same configuration, or would there be a spectrum of configurations even within the same theory?
So even within the same theory, there will be a spectrum of configurations, but it turns out that there will be, within that spectrum, if you wait long enough, there will only be certain ones that will survive long. Okay. So initially there'll be a spectrum, but there are certain ones that just have a very long lifetime. So what happens is that the other ones essentially migrate to this long-lived one. They evolve to this long-lived one, then hang around for a while, then migrate out of that and decay away. So it's like there's an attractor basin of sorts where they end up getting collected.
I see. All right, thanks.
There's the other thing, Raymond, which is important, is that initially when you produce them, you produce sort of all sorts of, you produce them based on whatever the dominant instability in the field was. That's a scale of these objects, right? The length scale that was there. And once they form, though, that there are also things like just stability. They're being perturbed by other things around them. So some of them are unstable to perturbations, but some of them are not. So you they self-select, and then certain configurations and certain characteristic scales survive. Everything else sort of goes away. So you can form them, but they don't survive very long.
I see. Thanks.
So you mentioned, sorry, I think you mentioned earlier about this gravitational conformal coupling. I mean, in the effective field theory there, I would have expected this coupling. So, but you said that it doesn't really affect anything. Is that right? Would it affect, say, gravitational production?
So that it could affect, yes. So what I meant was the electromagnetic production is
sure, yeah.
More effective. So yes, that it could affect. I haven't explored that at all.
But do you know like how it would affect it? In what way will it enhance the?
That's a good question. Let me see.
Because this coupling in principle should be there. It's a dimensionless coupling, can easily be order 1.
That's true. That's true. I don't know.
But then you can redefine your fields, right, to get rid of it, and then you end up with the same theory with a different potential.
I see. So you can just map it into the potential, probably.
That's true.
It's just yeah,
because it reminds me of the Higgs inflation people. That's what they do, right?
Yeah.
And in this way, they get a flattened potential, right? So it's like you add more.
I see. So it becomes more flat then. So it end up being much flatter potential.
Yeah. So you add more attraction between particles.
I see.
Yeah, but how does it affect? But I think that's just a statement. I mean, does it? I guess the question: how does it affect gravitational waves production, though? So I guess it doesn't. The claim is that in this sense, should it affect gravitational wave production or not? If I have the same configuration, right, it's the same theory. So physically, so I guess it's the same thing. When you're going from Jordan frame to Einstein frame.
Yes. No, I mean, the potential is different. So configurations, stable or Link configurations, they may be different as well, right? So
yeah. Yeah, I always get confused between, when going between these frames, how to then think about the gravitational radiation part of this. Yeah, I don't have a quick answer, but I think I agree with Andre that at the end of the day, the theory can certainly be mapped, right? But I don't know how to think about the solutions then so easily. And what part goes into the gravity part and what part goes into the scalar field part then, right? Because you're mixing. So that part is what confuses me a little bit.
Thanks.
Any more questions?
I'll leave this. I think, have you guys had a talk by either Anson or Curly or Pratik about this? No?
Not about this. Anson did give a talk, but
okay.
Yeah.
So I didn't mention this, but
yeah, if you want to take a few minutes to tell us.
I'll just think. I think it's a cool thing. I mean, it's not to take up too much time, but so about a year ago, I think the authors that I just mentioned had what I thought was a really neat paper, which was basically saying that, look, if you take ultralight axions, whose masses are, in this case, they're not dark matter, right? They're so light that their mass is basically less than about 10 to the minus 28 eV. It's a really ultralight ones. Then it's possible that they could still have strings, string loops present in today's universe. And the interesting thing is that because of this coupling, the usual axion-photon coupling, if light passes through these loops, you get a rotation of the polarization of light. And this rotation, again, people know about this rotation from before, but there's a definite amount of rotation based on when they go through loops or whether they don't go through loops. So what one can do is then think about using the CMB as a backlight and try to see if we can see patterns of this rotation in the sky and use this to probe whether we have an axion string network or not.
How big are these loops?
So these loops, the simple answer is we don't know, but typically simulations show that they're in scaling, okay, which means that there are some fraction of the Hubble radius. The dominant loops are some fraction of the Hubble radius at each scale. So the loops are not remaining, the loops are merging and connecting together, but they're in a scaling regime. So there's some fraction of the Hubble size at each Hubble time. So it's just like the network looks the same at each time, essentially.
So, but then if you're looking, then a huge patch of the sky is going to be inside a loop or outside a loop, right?
Well, yes, but you also have the light has passed through many loops before, right? So you could be inside one loop, which that doesn't matter, right? But because you've passed through many loops, you will get sort of a random walk of polarization changes passing through them, right? So if the loops are oriented one way, you get one direction. If the loops are oriented the other way, you get another flip. And you can imagine constructing a random walk of how the polarization is shifting back and forth a bit, right? Meaning rotating one way or the other.
But do you know original polarization distribution? Let's say there is no any kind of change of polarization. Do we know what we started from?
Well, I mean, yes. Well, we do in some sense because we measure that polarization in the sky if there is nothing going on, because this is just
no. I mean that if you are trying, you are measuring it, but I mean, I wonder was it defined by kind of initial conditions, or say, I mean, when it was produced, say this, it could be already have some pattern. So that's why I wonder.
Right. So Arkady, the thing is that it is true that we can't, in principle, know what the initial conditions precisely were. They are what is expected in the CMB from the temperature fluctuations.
Yeah.
But the reason for this, but you can still measure this effect, because what you're going to measure is 2-point correlations, and there'll be rotations, there'll be patterns of rotations which will convert, for example, the E mode polarization partly to B mode polarization. Okay, so the rotation of these polarizations produces coherent changes in the polarization, which you would not expect to have directly in the CMB.
I see. So there would be correlation because if it's say geographically close, right? It could be the particular correlation.
It would be exactly. So it would be correlations in the rotation patterns in the polarization that would be an indication. And more importantly, it's really correlation. The way these observations are going to be done is they're going to look for correlations between the E mode polarization and the B mode polarization, which cannot be produced easily. Okay, so this produces a correlation between them that can be then looked for in the CMB. And people are already sort of looking for this in Planck data and so on. And what's exciting, at least what attracted me, Andrew, and Mudit to this was just that this effect is independent of this tension in the string. It's not a gravitational effect, right? It's independent of the tension in the string, which is what most people have been looking for in this context. So this is why I think this is they called it sort of, the Berry phase-like effect. So that's what I think is quite cool about this.
What about looking in the directions of quasars? So it's a lot more local.
That's true. I think they tried to look for. I forget what they found. What they found based on that. I would have to look. They did talk about this in their paper, but I think it was not so promising for some reason that I can't remember why.
And you would at least get rid of the idea that it's passing through different loops at different times, because you have only redshift of 3 that you have to go back to.
True. But I don't know if it's that's true. It could be that you could get a coherent signal over a larger region there if it was only passing through one. I agree with that. But I forget what was their reasoning for why it was not so not the best thing to do. But maybe I'll have to look in the paper again, Keith, to see what their reasoning was. We didn't do that. We only looked at the CMB. And one of the things the thing we did, which was different from them, is not so much that we introduced any new physics from what they had done, but we just tried to build sort of a calculational framework where somebody gives you a model of the loop distribution, which is not completely known. So instead of just assuming that the loops could be in scaling, but you could also have many distribution of loops sizes. And those would correspond then to different power spectra of this rotation on the sky. So it leads to different shapes for these things, right? Different shapes for the power spectra on the sky. And you can even distinguish whether this network had collapsed at some point, network of loops collapsed at some point or not. And it could be an interesting thing, I think, to look for in current generation of detectors as well as future ones. And it seems that you could have sensitivity. Of course, we're all—
Does the rotation depend on the angle of incidence with respect to the plane of the loop?
No.
So just going through the loop is
just so if it's basically because the axion field is changing from 0 to 2 pi, right? From one side of the loop to the other, right? So that's what. So it's as long as you start sufficiently far from the loop and you are measuring sufficiently far away from the loop, the rotation is this A times alpha EM, which is just this quantity here. Okay, so it's a definite number each time. So that's what I think. Now, of course, you don't know this. So this number in radians is small, right? It's not going to be a large number. Alpha EM is 1/137, right? So it's not a large number. So every time it's going to, if it passes through many loops, it's going to be a small rotation in each direction. But the rotation is not going to be a humongous one for each loop. So that's why I was talking about this random walk that you can accumulate or you can wash out, depending on how this happens. And the way it accumulates is if you are going through this, if your light rays are going through the same loops, both your light rays are going through the same loops, of course it accumulates. If it's going through loops that are separate on each trajectory, then it doesn't accumulate, it washes out. But this is, I think it's a neat idea that these authors had suggested. We're just sort of building up on that to try to generate something that can be then observationally, we can look for it in the CMB.
And now that you're talking about it, I think we had a talk by Curly 2 years ago.
Okay. Yes, I think, yeah, they started doing this about 2 years ago, and they published, I think, maybe a year ago. Maybe, actually, sorry, it was 2019. This last year has been a wash. So that's right, it was about 2 years ago.
It feels like yesterday, but
Yeah, that's right. That's when they had it. It's 2019. That's right.
Could you say again what you meant by the source of signature in light?
In which case?
Well, in the late universe, in their final summation.
Oh, this over here. I see. This part, source of signature in light. So what I just meant by that is that typically, so dark matter, of course, if say these axions are dark matter, then we are looking for signatures of this dark matter in light, because we are looking for where these objects collide with each other, or whether the solitons made up of the dark matter enter regions of strong electromagnetic fields. They would create radiation, which we can then probe with the help of light. That's what I meant.
Okay, thanks.
Yeah, but going back to axion loops, I mean, how unique is this signature? I mean, can there be something else that gives more or less the same effect, like magnetic field, for example?
I think it would be, I'd be hard pressed to say that you would get a spectrum that's shaped in this way, this almost scale invariant structure. It doesn't look scale invariant on this plot, but it doesn't change much, right, on these decades of scale. And this is pretty large L's here as well, right? Sorry, small L's here as well. So again, it's possible that you could have some magnetic fields, it's Faraday rotation, the usual Faraday rotation, that could do this as well. But I think
yeah,
that's
how people look for it, right? When they look at quasars, for example.
That's right. So you could certainly, but I think maybe, Keith, that might have been the thing, that maybe the Faraday rotation just wants stuff in the middle over there. The usual Faraday rotation when magnetic fields are on quasars gives you a lot of sort of concern about whether you can disentangle this effect from there or not. Maybe that might have been the reason. But I have to look again. But so, Andre, to answer your question, yeah, I have to think how degenerate it would be with that. But if you have a spectrum like this, and if you can measure the spectrum, I would be surprised if the spectrum is the same for magnetic field distribution, right? So you could distinguish it from that spectrum rather than just by, if you're looking for a single homogeneous zero mode signal, then I think you wouldn't be able to distinguish. But if you're looking for the spectrum, I think there'd be information here. That's the thing. In general, all that is happening is that the scale that is picked out by the spectrum is the size of the loops that are present, the dominant size of the loops that are present at the time of the CMB. That's what sets this scale here, okay? Where the spectrum peaks. So that's the scale where this would be. Everything else is sort of just that is the main physics scale that enters here.
Okay, any more questions? I'm gonna stop recording.